Okay, now chapter 3 is focused on the learning outcome number 2, where you need to learn about losses. So in previous class, we stopped at equation for your Q, for your flow. Let me see. Previously, yep, we talked about this ratio, about PL, pressure, length, the shear forces divided by R. In this case is stress, shear stress. This is shear stress. Okay, let's pick up from here. So previously we learned about this ratio. Okay. And we stop at these slides, right? So here we prove that the parabolic flow is given by this equation with the shear stress at the wall, diameter of the pipe, the dynamic viscosity. This is dynamic. We have two kinds of viscosity in the table that you see in exam. One is kinematic, one is dynamic. This is dynamic, dynamic viscosity. 1 minus R divided by R. So R is the outer radius R here, right? Okay. So today we're going to continue looking at this equation, right? So how they're going to apply F equal to MA in our float, in our fully developed laminar flow. On the right hand corner here, you are seeing the equation that we covered in previous lecture, which is U equal to this one, okay, in terms of ratio of your R. Okay, and also we can rewrite this equation in yellow in the white color one, meaning we are replacing the shear loading, shear stress at the wall times diameter of the pipe divided by 4 times dynamic viscosity. This one will equal to the velocity at the center. Okay, this term equal to VC. VC is a velocity at the center. Okay, now normally in pipe, because center there's no surface that created friction, we will have a maximum velocity at the center of the pipe. Okay, yeah, so this is the logic thinking when you solve pipe flow. They're always maximum at the center, and then as it touched the wall, the liquid or the water touched the wall, the velocity stop at the wall, so there's no velocity there. Okay, so next we're going to look at how we derive the Q for pipe. Okay, so if you look at the diagram on the left hand side, you have a cross section of the pipe that you will see a circle. All right, the dot here is the center of the pipe here. All right, the dot, and then we have a small r and r. Okay, small r and r. R is the radius at that particular location. Capital R is the outer radius. All right, and if you study about circular area, dA means the small changes of A or the highlighted purple color or yeah, this colored zone here. dA equal to 2 pi r dr. Okay, so this equation you can find in your advanced mathematics when you calculate small changes of area in the circular. All right. So recall what is definition of Q. Q equal to velocity times area. Okay, previously you look at this one when you study m dot. M dot equal to rho AV, rho Q. So AV equal to Q. So when you want to calculate Q by using the diagram on the left, what you take is that you integrate the velocity times the dA. Okay, U times dA. So in this case, your A is changing. So the one that you can integrate is the area. Velocity will be the same. Okay, or not same lah, but velocity have the equation for that. That replaced by this one. Okay, by the equation at the bottom right hand corner of your screen. So you integrate of dA. Then move on. You start developing the equation by expanding the dA into 2 pi r dr, what you can find in the diagram. Okay. Then you do integration by substituting what is your u, you pull outside, you put outside of the integration. All right, and then you pull the 2 pi outside there. So you get 2 pi Vc integration of the ratio of your r. You get this equation. Okay, so this development equation, you can look at the slides. Huh? So later you can come back to these slides. Then after that, when you get this equation, you can write Q equal to 2 pi r square Vc divided by 2. Okay, so we're going to use the average velocity in this case. Previously, we covered how to convert the parabolic equation flow into uniform flow. When we cover chapter 2, right? There's a particular section we discuss how you convert parabolic to distributed or uniform flow. So in this case, if you look at the screen here, so Q equal to VA, like we discussed just now. So we're interested to put in terms of V, so you move your A to left-hand side, become divide, Q divided by A, you get V, right? So how you get your area? Area is, because in this case, we are having a pipe having a circular area, so you use pi r square, okay? By having that, you rewrite the equation above, meaning you see here, V equal to QA. Then you substitute what is the Q definition from above inside here. The A is 2 pi r. So you'll get this form. Pi r square Vc divided by 2 pi r square. And you cancel this one, cancel this one. You'll get Vc divided by 2. And you know that your Vc equal to delta Pd squared divided by 32 mu L. Okay. And you further, let me see, Pd. Okay, so your V is in this term. Okay, V in this term. All right. Now, how you get this one? You need to recall the definition of Vc in the previous slides. Okay, the definition we talk about the ratio of P and so on. Okay, then you substitute here. After you get your V, you rewrite your equation in terms of pressure, diameter, dynamic viscosity, and length, meaning you rewrite your Vc in this term. Then at the end, you arrive at a very important equation for Q for pipe. Huh? So this slide is important when it comes to your test or final exam. When you need to calculate the volume flow rate, Q for pipe. So you need to find the change of pressure. Delta P means you're having a 0.1, 0.2. So you're given pressure 1, pressure 2. And again, pipe flow, remember the mechanism that make the flow flowing. The P1 must be higher than P2. Huh? So higher pressure move to the lower pressure. So the arrow is pointing from the left to right. There must be a change of, there must be a pressure differences between 2 points. Then the flow will be able to flow. Okay, so this equation tell you the volume flow rate is affected by a few parameters: D, pressure, viscosity, and length. Okay, so by looking at this equation, Q equal to pi D power 4 delta P divided by 128 mu L. So you should able to explain what happened if the engineer accidentally use a smaller diameter, what happened to the Q, if the pressure drop, what happened, the viscosity, if you increase or you reduce, what happened to the Q, if you increase the length of the pipe, what happened to the Q. Okay, so by looking at this mathematics model, you able to explain these 5 parameters, including the volume flow rate. Right? Now, for example, you need to maintain the Q. And then, for example, the diameter change. What else you can change to maintain the Q? This kind of question you need to know on mathematics using this mathematics equation. Okay, again, I stress this one is important for your test and final exam. Next, you're going to move on. So again, Q equal to pi D power 4 delta P equal to 128 mu dynamic viscosity divided by L. All right. Take note of this statement. This one, Q equal to pi D power 4 delta P divided by 128 mu L, valid only for laminar flow. Okay, take note. Meaning, if you solve the question, you try to find the Reynolds number equal to something. From there, you can tell whether it's laminar or turbulent. If laminar, you need to find Q, you use this equation. If turbulent, don't use this one, because this equation only apply for laminar flow. It is the magic number 2100. This is also called Porcelli law. This Q equation, Q equal to this dP mu L relationship, this whole thing is called Porcelli law. Okay, take note. You might need this word when it comes to your lab report later on. Okay, you might need to explain why you can use Q equal to this one in your report. Keyword laminar flow. Proof that in the experiment, your R is less than this one, then you can use this one. Okay. All right, now we have clear for horizontal pipe with 0 degree. 0 degree, meaning going along x-axis. Okay, so all the equation you learned so far is for horizontal pipe. Next one, you look at the diagram. Something changed to the pipe angle. There's an angle there. Okay, so this is the horizon. This is the horizon. Okay, horizon. The same pipe characteristic that we discussed previously, only differences is now we change the angle. You change the angle, something changes to the equation here. As you can see, if you change the angle, W axis going to take place. This one must add it to your equilibrium equation of force. All the force equal 0. So when there is an angle with the horizontal, remember there is a W or weight of the fluid happening. Okay, W. So as you can see, this one same, this one same, this one same. Okay. Now if you watch the diagram, something different from the notation here. This is 0.1. This is 0.2. Okay, and point 1, given you the pressure at point 1, P equal to plus pressure, point 1. Point 2, the pressure is P. Okay, cool, are you there? I'm still asking you the same question that I asked you since the beginning of the chapter. I'm going to ask you the direction of the flow. By looking at the delta P, P plus delta P at point 1, P at point 2, assume delta P is positive. Cool, what is the direction of the flow inside the pipe? For example, this is point 1, this is point 2. What is the direction? Is it go up or go down? If your delta P is positive.
Go down.
Why?
Because 2 to 1.
Which one higher? You tell me, which one pressure higher? Your delta P positive value.
The positive.
So point 1, point 2, which pressure higher?
1. Pressure 1.
Pressure 1 higher.
Yeah.
More than P2, right?
Yeah.
So how the flow? The flow from high pressure to low pressure or low pressure to high pressure?
High to low.
High to low. So it moved from point 1 or
1
1
to 2.
to 2.
2.
Okay, correct. So again, the changes of pressure will decide the direction of the flow. So just now, Ku answer earlier is not correct, but the later one is correct. Okay, by looking at the pressure component, you know the direction of the flow. That is more important. Okay, the earlier slides that you see, the same meaning also. The earlier slide, the P is here, but the point 2, it gives P minus delta P. Same meaning. It means that if P a positive means point 1 still higher than point 2. Okay. So you're able to understand the direction of the flow. Sue, are you there? Not Sue, sorry. Sue is from other class. Dinesh, are you there?
Yes, sir.
So do you understand the direction of the flow?
Yeah.
Okay, good. So as you look at the diagram, I think self-explanatory means you're able to understand why this one direction going down, this one going up, this one arrow pointing in, and the weight is pointing down. Okay, again, just to stress one more time, pressure always acting on to the surface. Okay, pressure. But you're looking at force. So convert pressure to force. How to do it? Recall pressure definition. Pressure equal to force divided by area. You want to find force, you take pressure times area. Okay, yeah, that's why the arrow is like this. Shear always opposite the flow direction. Gravity always pointing down, so that's why W is pointing down and with the angle. So the angle will be the same of the rotation of the pipe or orientation of the pipe. This angle will be the same as this angle. Okay, all right. Why we need to learn about this one? Because this is popular question either in test or final exam. This we expect you to derive from the question. You'll be seeing something like this diagram. You need to know how to draw this diagram. Ask yourself, if the pipe is slanted like this, I give you an angle like that. The diagram will be different if I change the angle and rotation. If I do like this, are you able to redraw the free body diagram? Yeah. Okay. So this diagram is when you learn static already. So I'm not going to repeat this one. So you have your W sine theta over here that can add it to the system because we are looking at X direction. Okay, yeah, we are looking at X direction. We are looking at all the force in X direction equal 0. So this component is sine theta, W sine theta. How do you find the W? You use this equation, which is this is the specific gravity times the volume. Okay, this one gamma is specific gravity which in the unit of kilogram, not kilogram, Newton over meter cube. So you take this one, gamma times volume, you get Newton. Okay, but in this case, there is a slanted angle, so sine theta. All right, so take this one as your homework. Try to ask yourself whether you know how to derive this diagram to this free body diagram. This is called free body diagram. Okay, free body diagram. Ask yourself, huh? Right. Then after that, I put side by side the diagram together. Earlier we learned about this ratio, delta P divided by L equal to 2 shear divided by R. This is what you learned in a horizontal pipe, right? You learn in horizontal pipe, and the flow from the left to right. You learn about this equation. So when you slanted at a certain angle, and this angle is anti-clockwise direction, okay, this direction, so you need to do something on the equation. You change the left-hand side to right-hand side, meaning you add a negative rho L sine theta. Okay, there's a derivation that you can prove this equation. You repeat the same, only you add in the weight like this one to all the force in X direction is 0. You will arrive at this equation. Delta P minus gamma, this is specific gravity again, Sg, specific gravity. L length and sine theta is the orientation of the pipe compared to the horizon axis. And we take it as anti-clockwise as positive, the angle. All right, so we get this equation. So this simplified, I think 5 pages of textbook into 1 slides here. Okay, so this is horizontal pipe. On the left hand side, right hand side is slanted with an angle. You just need to add the orange color equation inside the equation. Same with the velocity. Just now, we also proved before this in the horizontal pipe scenario, we get V equal to this one. So what you need to do is, the differences is there is a changes of pressure component. Okay, pressure component change when you change the orientation. So the V will become this one. Okay, this one change to this one. There's a negative there. Okay, Q also same, change to this one. Change the pressure component to this one. All right. Yeah, again, I'm not going to go through the development of the equation. You go back to the previous slides for horizontal. Now you use this diagram to derive the equation. At the end, you will see these 3 equations. This one, this one, this one. Okay. So this slide also important for you to refer when it comes to test. Make sure you use the correct side. Left hand side for horizontal, right hand side for slanted pipe, or there's a orientation of theta. Okay, yeah. So I said put a note there for you also. What happened? The flow is downhill. This is uphill, or left-hand side is uphill. Uphill, what does it mean? Water flow from the bottom to top of the mountain. You imagine this one is top of the mountain, you go uphill. If the scenario is a downhill, what I mean by downhill? It means the flow from the left to right. Downhill, I will change the color of my pen. Downhill is this one. This is called downhill. When the flow from the top of the mountain to the river, we call it downhill. So downhill, sine theta will less than 0. Okay, sine theta will less than 0. Just take note on that. Okay, so you take some time to digest these slides. What is important again, look at the changes of pressure. What happens if you are slanted like this? This is an uphill scenario. However, when you have a downhill, then the value of sine theta will be negative. All right, meaning this one will be negative, negative, negative. If it's uphill, this component is positive. Uphill, positive. Huh? Downhill, negative. Okay, again, stress this slide is important when you change the angle. So uphill, positive. Let's look at one tutorial question on application of equation that we learned so far. So this question will be the same as your tutorial question. I think this one is question 16 in your tutorial. So let's look at what happened, what to need to solve. So you are given, maybe sometime you're not given any diagram at all. You're just given a statement like this in your test. So you're having an oil, you're giving the oil that let me change my, you give flowing in the pipe, you're having an oil. You're given the viscosity of dynamic viscosity equal to this one. Mu is given, density is given, diameter is given. So you're having mu, you're having rho, you're having d. You need to find the pressure drop or the delta P to produce a constant flow Q. Q is given if pipe is horizontal. In this case, your pipe is horizontal. So there's a slide just now that show you what happens if you have a horizontal case, what happens is non-horizontal case. So for section A, the pipe is horizontal with a length given here. X equals 0, x2 equal to 10 meter, means the length of x1, x2 is given. So when you did a little calculation for L, you score 1 point. L equal to x2 minus x1, you score 1 point. Very easy, yeah? And then the B1, what happened if you have a steep hill, there's an angle given, what happened to you need to find how steep of the hill must the pipe. So you need to find the angle so that the flow same, means Q maintain. Delta P maintain. So what can you find for the theta? C for condition, part B, after you find B, given the pressure at 1 point, what is the pressure at section particular length of 5 meter? Okay. So there are two scenarios. One, horizontal pipe, find the delta P, this is A. Second, at what angle of theta? The Q maintain. P, delta P maintained. This can achieve by what angle? This is B. C, it asks you, slanted pipe also, it asks you what is, let's say this is 0.1. It asks you what is your X number 3, 5 meter from X. This is 5 meter. What is the condition of pressure here? What is the P number 3 here? Okay. All right, how we solve? First, identify parameter. Second, call out the equation. So we want to find delta P, go and look for delta P equation. In this case, since you're given the Q, go and look for Q equation. And remember, this equation only works for Reynolds number less than 2100, which is a laminar flow. Okay, laminar flow. So you have this equation, you have the Q, you have the D, you have the mu, you have the length. So with this equation, basically you have all the parameter, you have D, you need to find this one, Q given, mu given, length given. Length you calculate from x2 and x1, rearrange, you get delta P. Okay, make sure the unit correct. This is this one. So I'm not going to show you the step, the detail of the numbers that you should get, but I show you the steps. Okay. Just to cross check for this exercise, for this tutorial question, delta P for A, you should get around 20.4 kilopascal. For your test and final exam, give at least 3 decimal place if you need to answer the question. Decimal place, 3 decimal place. Any question for these slides? Anything that you're not sure? Why we can, if you're not able to answer why, how you can get delta P equal to 20.4 kilopascal for section A? Ask me now. If not, I might ask some of you to answer. You're not sure, better ask me now.
No question, sir.
Okay, good, Shirley? Okay, good. Okay, let's move forward. B, what happens when you have a need to tilt the pipe by maintaining the Q? So again, use the one that related to the slanted or angle. There's something changed with your pressure component. You use this one, minus specific gravity, length sine theta, substitute, and this is uphill. We assume uphill. So set sine theta 0. This one component is positive. All right, and no pressure drop. There's no pressure drop, meaning the delta P is 0. Okay, it asks you how steep a hill must the pipe be on if the oil is flow through the pipe at the same rate, but with P1 minus P2, meaning maintaining the change of pressure. So you rewrite. So this one, the next step will be the delta P0. So you only left out some of the component. You rearrange, you get this equation. You have the Q, you have the D, you have the G. Okay, G again, don't use 10. Gravitational acceleration, you're in your third year already, use 9.81. Unless the question gives you G equal to 10, then you use 10. If the question you didn't see anything mentioned about the gravity value, straight away use 9.81. Okay. Okay. So you substitute, you use your calculator, you manage to find theta equal to negative 13.34. What I mean by negative? Okay. What I mean by negative? Okay. Okay, look at the slides. I give you 10 seconds. Why your answer get negative? Is it logic or not to get negative? To maintain the flow at the same rate Q compared to the section number 1. Means there's no change of pressure. Because just now, section A is the horizontal one. Now you tilt uphill like that. And you calculate is negative. You calculate the angle is negative. And we already defined just now what is our positive direction. Our positive direction is from horizontal anti-clockwise. But now you get a negative sign. What does it mean? It means in real scenario, it cannot go like this way. Your pipe cannot go like this way. Okay? But your pipe should rotate this way. The angle is going this way. That's why you get a negative sign there. Your flow is flowing from top. From the top to bottom. Spend 10 seconds to think about logic or not. You get negative angle. So you try to imagine. You want to contain the Q. You want to maintain the Q. You should rotate the pipe in a negative angle so that the Q and the pressure doesn't change. Does it logic? Try to think. What happens if you if you calculate positive? Is it possible you maintain the Q? Is it possible you maintain the pressure if you have a positive angle? Think about that. Huh? All this might come up in test. Okay, you try to imagine if you want to push some liquid uphill, it will be difficult. If you have an uphill like this, the angle is positive. The pressure the velocity going to get slower and slower. Everyone need to climb uphill. All right, so you're not able to maintain the Q. So, however, because it's negative, the gravitational force is added to the system. You can maintain the Q and the pressure by having a negative angle. Okay, don't confuse with this negative and this negative. Huh? Don't confuse with this statement. Don't confuse. Huh? Don't confuse this. Right. Okay, just to test your understanding in just to test. This is horizontal. This question I'm going to ask. Raj, are you there? Raj?
Yes, sir.
Okay, I'm going to ask you this question. This is horizontal, theta 0, right? So, if I have a pipe orientated like that, if I want my flow to flow uphill, my question is, let's say this is 0.1, this is 0.2. You want this water go uphill. What is the condition of pressure you need? in this case? Which one you need higher? Raj, try answer.
So which one is higher?
You tell me lah. Or I will ask Ku to answer for this question. Ku is expert already in this question.
Yeah.
Okay, I repeat the question. Now you're having a pipe like this. Going like this. Okay, you have two pressure there. Pressure 1, pressure 2. Now you want the water go uphill. You want the water go uphill. Tell me. Okay, Raj, you tell me. Pressure 1 should be higher or pressure 2 should be higher? What do
So
you think?
I think pressure 2, sir.
Pressure 2 higher.
Ah,
Cool, can you explain to Raj?
The pressure one must be higher, and then the P2 must be lower.
Why? Why P1 must be higher?
Because the pressure one
How pressure works? How pressure works? Pressure move from what to what?
to
Pressure.
from P1 to P2.
Okay, so pressure move from higher place to lower place. Then it will push the flow.
Yeah.
Raj, do you get the idea?
yes, sir.
Okay. Right. Raj, I'm going to repeat the same until you expert like cool already. Okay.
Sir,
Yes.
sir, can you repeat, sir? I got disconnected just now. I keep on
Repeat what?
disconnecting, sir.
Who is that? Dinesh, is it?
Yeah.
Okay. All right. So just now I just test a concept. You have two cases. One is horizontal part like this, where your theta is 0. You understand? This one is horizontal. Now, if you have a case, you don't know the pressure between 2 points, but you have the direction of the flow. Okay, let's say this is point 1, this is point 2. You have pressure 1 at station 1, pressure 2 at station 2. But now you know the direction of the flow. It is your Q. You know that Q is flowing uphill. Uphill means you pump water from low level to high level. Okay. Dinesh, you understand about the direction?
Yes, sir.
Okay. Now I'm asking your friend just now, by having this scenario, what is the pressure setting that you should have in your system so that the water can flow uphill? So that the water can flow from low ground to high ground. So the principle of pressure, it works from high pressure, you will flow to low pressure. So by having this concept, P1 must be higher than P2. Do you get that, Dinesh?
Yes, sir.
So by looking at this, just now I asked your friend, what is the setting that you should have? P1 higher or P2 higher? So the answer is P1 higher.
Yes, sir.
Okay. All right. Once you understand this one, you should manage to solve a lot of part problem. Okay. So this one I explained already, the angle. And also at the end, you get the answer is negative. So you should able to understand why negative can maintain the same Q and P by recall back what I asked you just now, right? How the flow can flow. Okay. Then condition C, what happens if you're given the P1 pressure and you need to find the condition at x equal to 5 meter. So having the angle calculated just now, right? In this case, do you see any length inside this equation? There is no, right? Just now the equation. How you find this one? Okay, in the previous slides. So in step number 2 or B, you already calculated using the Q equation. Q equal to this one. All right. And why you use this one? Because this one, your pipe slanted with the angle. And you assume it is uphill. You assume it's uphill. And you assume uphill means the flow go like this. Go up from low to high. Low ground, low ground, not pressure. Low ground to high ground. Pressure, high pressure to low pressure. So you use the negative something, negative minus this one, and you rearrange, you cancel out the length, you get this one. So by looking at the sine theta equal to this, all these parameter here, there's no length. So what does it mean? And okay, let me go back to the general question just now. Okay, if you look at this, all this question, A, B, you solve. Question C actually is a trick question. Remember the Q that you calculate, that you use, Q equal to something 128 mu delta P mu something, this equation, or this equation. This equation works for laminar flow only. What I mean by laminar? Meaning the flow inside the pipe is always same. Okay, the velocity inside the pipe always same. So by having this concept, or you look at the equation that you derive from step number 2 or B, sine theta equal to this one. Inside here, there's no length there because you no need the length. So it just means that the pressure doesn't change. Okay, if you're given the pressure at a certain point, P1 will be the same as along the pipe. Okay, along the pipe, meaning because this question is taken from B case, B is a slanted one, and the delta P that you calculate for section B is 0 because you need to maintain the Q, right? You need to maintain the Q. So to maintain the Q, there is a calculation there, and you come up with this equation, sine theta equal to this one. However, in here, there's no length parameter you need. It just means that the pressure drop or the pressure quantity inside here will be the same as P1. Okay, the argument is pressure is constant along the pipe. Okay, and the slope of the hill is constant, meaning you have a constant upslope. Okay, theta. So this is how you apply the equation for the horizontal and the tilt one. So just back recap. So this slide is important. This slide is important. Left hand side, horizontal pipe. Right hand side is for the orientated, or there's a tilt angle. This angle, there's a note here. If it's up downhill or uphill, something different to the sine theta here. Uphill, positive, means if the flow uphill, this component positive. Don't confuse with the negative in front. This sine theta is positive. If it's downhill, because downhill is negative theta, so you will get sine theta equal to negative theta. You'll get negative value if it is going down like that. Okay, just take note on these slides. So I think we're done with this one. Okay, let's go for a short break, 10 minutes break, then we continue with the Navier-Stokes equation and so on. So we stop at this slide. Let me stop the recording.